right, so in today's video, we are taking a look at roots of polynomials. And so far we have worked on factoring and using synthetic division to break polynomials down. We spent some time looking at factored form and how we can get down to that, similar to how we did with quadratics. Now we're going to take that a step further and talk about how we can identify the roots of the polynomials, which directly relate to those factors. So our goals for today are to anticipate how many real roots a polynomial should have and where to find them. And then from there, use the rational zeros theorem to find roots, as well as synthetic division to find any additional roots. And if we have time, we will look at how we can verify our work by using Desmos graphing. So our first item today is in your book on page 279 called Cauchy's bound. And remember, we're working on practicing reading theorems and reading the way that we have mathematical symbols and terminology. And so I want you to make sure you take time to read through this theorem on your own. And what I'm going to do is just describe to you how this theorem works. So what Cauchy's bound helps us do is determine the interval in which we'll find all of the real zeros or roots. Okay, and so we have this little formula here, but we have to find m. Okay, and so m is going to be the largest of the numbers that we get when we work with the coefficients on all of the terms along with the coefficient on the first term. So it's pretty easy. All we need to do is take the absolute value of each of those coefficients, so that's just the positive form of those numbers, and divide it by the absolute value of that leading coefficient. So we have 3 divided by 2, 6 divided by 2, 1 divided by 2, and 4 divided by 2. And to more easily compare them, let's just go ahead and write them as decimals or whole numbers. And so we have these four numbers, 1.5, 3, 0.5, and 2. So what this theorem says is that the largest of those numbers is what we'll use as our m. And then we can go ahead and apply this little interval formula. So all we need to do is take m plus 1, and we take the negative version of that and the positive version of that. And so that gives us, for our example here, the interval of -4 to 4. So we should expect any real roots that come from our function to lie between -4 and 4 on the x-axis. All right, the second item is called Descartes' rule of signs. This is also going to help us determine what kind of roots to expect. So we're still not going to know what the roots are yet, but we'll get there next. This is going to help us look at, do we have positive roots or negative roots? So here we had an interval. Here we'll be able to kind of narrow down on which side of the y-axis will we find these. All right, so again, I'll let you read the formula start to finish on your own, but here's what we're going to do. We're going to work with both the original function f of x and f of negative x. Now note that this one actually hasn't been changed over here to look like that yet, but we're going to do that together. So we're going to start with f of x though. And all we need to do here is look for the sign changes that we have from term to term in the function. And for the positive f of x, that number of sign changes, or what are called variations in the sign, that number will be the positive real zeros. And that counts multiplicity, so that counts if we have, a factor that's squared. And then when we get that value, if it's big enough, we'll also subtract 2, 4, 6, 8, etc., as long as the result of those is positive. And so sometimes we may be able to do that a few times, sometimes we might not be able to do that at all. All right, so let's take a look. We obviously have a positive 2x to the fourth, then we have a positive 4x cubed, then we have a negative x squared. So from here to here, we have a sign change, so that's 1. And then you can see that from there to the end, we have still negatives. So we don't have any more sign changes. So for this example, p is 1. And then if we subtract 2, Then we're at -1. And P is counting something, right? It's counting the number of positive real zeros. So we need P and P minus 2 and all of those to be also positive. Otherwise, right, we can't have a negative number of something in this context. So we're just done with that one. Now let's take a look at P of -x. And so here we're going to together plug in -x and see how that changes this. Remember that even powers allow negatives to cancel out. So this will stay as 2x to the 4th. But then on our second term, we have x cubed. And so one of those negatives on the -x won't cancel out. And so we'll end up with a sign change here. So it will be positive 4x cubed. Then our x squared term will stay the same. Our x to the 1st, that's odd, so we'll have a sign change there. Oops, and actually I made a little mistake here. So actually 2 mistakes. This is good to point out. So this was supposed to be positive. It did not copy over correctly. And this one was negative. So let's go back and fix that. So our sign change here actually becomes negative, and then this one becomes positive. All right, and then our last term just stays the same. All right, so now let's go ahead and count those sign changes. So we have 1 here, 1 here, and 1 here. So a total of 3, okay? And now we can, since n is big enough, we can do n minus 2, which will be 1. If we do that another time, n minus 4, then we're in the negatives. So these are our 2 options. Okay, so we for sure, no matter what, are going to have 1 positive real root. And we will have 3 or 1. So you might think, well, that's not really helpful. But when we get into our coming lessons working with what are called complex roots, because we know that the roots relate directly to the overall degree of a polynomial, if we know that we have 2 complex roots, let's say, that kind of helps us narrow down then that we could only have 2 reals, okay? And so you'll see in the next few lessons how predicting these kind of things actually does kind of help us. All right, so now let's lastly take a look at how we can actually find the roots without having to immediately factor. And again, I'll have you read the formula. Now, in the last two slides, we were looking at real roots, which could be irrational or rational. But in this theorem is helping us find specifically any zeros or roots that are rational. Okay, so if we do have any irrational roots, we'll have to find them afterwards by dividing out some known factors and breaking it down further, and then we can eventually get to those. So how this theorem works is it tells us that if we take all the possible factors of the last term in a positive or negative form, so that's plus or minus 3 and plus or minus 1, and divide all of those options by the factors of the leading coefficient, which in our case will be plus or minus 2 and also plus or minus 1. So any and all combinations of those will give us possible roots. So we could have positive or negative 3 halves, positive or negative 3, positive or negative 1 half, and positive or negative 1, okay? So now from here, it's just a matter of testing. Now we could use synthetic division to divide out the factors. So for example, if x is 3, the factor we would divide out is x minus 3. And if this is in fact a root, we'd have a remainder of 0. But in this case, it's actually easier to just plug in. Our polynomial isn't too long, and our numbers aren't that big. So we're just going to plug in some numbers and check to see if we end up with 0, because that will mean we'll have a root. So I'm just going to test 1 first. Just because 1's pretty easy. Okay, and let's see. Okay, and so when we do that, we end up with, let's see. 6 minus 1, 5, minus 6, negative 1, negative 4, okay? So that is not 0, so 1 is not one of our roots. Let's try negative 1. Just like before, a negative input will change our sign when it's odd. Okay, and so here we have, let's see, this stuff, negative 3 plus 6 minus 3, and that does equal 0. Okay, so negative 1 is one of our roots. Okay, now we're kind of near the end of our time today, so what I want you to do as an assignment, since we've been practicing with synthetic division, is working with our function f of x here. I want you to divide out that root, okay? And then see if there are any more possibilities that we can divide out further. You can continue to use substitution to check some of those. Also keep in mind that just because we've used a number doesn't mean it can't be reused, right? Because we could have multiple identical factors. So don't, like, just because we already used negative 1 doesn't mean we can't use it again. However, we did eliminate positive 1 as an option, okay? Once you've done that, you should get to a point where you can eventually, with a quadratic, just solve that for any additional roots, and we might have some irrational ones here as well, okay? So for tomorrow, I want you to finish that out, and then what we'll get to in our next video is we'll look at how can we take these patterns that we know about what the end behavior looks like and where our roots are located, and visualize ourselves what the graph will look like. And then we'll go ahead and see how Desmos graphing can really help us completely understand and get a full picture of that graph and that function, okay? So that's where we'll stop today, and please reach out if you have any questions.